Come back. So let me remind you, logarithmic functions, the graphs are increasing. When base is greater than 1, the graphs are decreasing. When the base is between 0 and 1. Moreover, y-intercept is a vertical asymptote. As x approaches 0 from the right, the functions if either go to positive infinity or negative infinity depending on the base. Now, with this information, let's graph log base 2 x minus 3 plus 1. What do we do? First, consider the graph log base 2 of x. Okay. Then, for x minus 3, shift this graph right by 3 units to get you log base 2 of x minus 3. Now take this graph, raise this shifted graph up 1 unit to obtain the graph you need. Log base 2 x minus 3 plus 1. So you took log base 2, shifted it right 3 units, and then lift it up 1 unit. So that's your graph. Okay. Here is an example. Let base b be greater than 0 and base not equal 1. Find x approaching 0 log base b of sine squared x. Now that's tricky. I'm saying x approaching 0. All right. So notice I could approach 0 from the left for all you care, right? But the point is, as x approaches 0, sine squared, because of the square, it approaches 0 from the right. Okay? Sine is a continuous function. So as x approaches 0, sine x approaches sine 0. Sine 0 is 0. But sine squared x approaches 0 from the right because all these values are positive. Now that's the important point. So you need to find limit x approaching 0 log base b of sine squared. It should be squared there, right? Let's fix that. Okay. Yes. Sine squared is negative infinity if base is greater than 1. Aha. So what happens if base is greater than 1? These are the examples. When you approach 0 from the right, you're going to negative infinity. When base is less than 1 and positive, of course, when x approaches 0 from the right, you're going to positive infinity. So that's what you need to worry about. If base is greater than 1, your limit is negative infinity. When base is between 0 and 1, your limit is positive infinity. Okay? Now, here is an important theorem. If base is greater than 1, the function fx equals log base b is a one-to-one continuous increasing function with domain 0 to infinity. This we just saw. All right? Range is the set of number line. Now, if xy are positive and r is any real number, then log base b xy is log base bx plus log base by. Log base b x over y is log base b of the numerator minus log base b of the denominator. Log base b of x to the power r is, the power jumps out, r times log base b x. Now the first part, why is log base b 1-to-1? Well, this is an inverse of exponential function. So remember, exponential function is one injective. Therefore, the inverse is also injective. It is continuous because your exponential function is continuous. You see, you are taking a reflection along the line y equals x. So if one graph is continuous, its reflection is also continuous. Increasing function, again, we just saw that it is increasing if base is greater than 1. You can see it using your graph, or you can argue using the fact that log base b is the inverse of exponential. All right. Now, basically, you need to use the graph here. All right. So now let's show these three rules here. Log base b xy is log base b x plus log base b y. Well, to prove this, what do? Let P be log base b x, Q be log base b y. What does P equals log base b x mean? B to the power P is x. B to the power Q is y. That's what these two mean. What does that mean? Base b to the power P times b to the power Q is x times y. Why am I doing multiplying? Because that's the goal. I want to multiply x, y. So, when I multiply powers, you see, so I have the same base, the exponents add up. B to the power P plus Q is xy. What does this mean? This means log base b of xy is P plus Q. P is, remember, log base b x. Q, if you remember, is log base b y. In other words, log base b xy is log base b x plus log base b y. Okay. Similarly, we'll prove the next one for the quotient. Let P be log base b of the numerator, Q be log base b of the denominator. This means b to the power P is x. This means b to the power Q is y. So when I take quotient, b to the power P over b to the power Q is x over y. This means b to the power P minus Q is x minus y. That's what happens. You have the same base, different powers. So what does this mean? This means log base b of x over y is P minus Q. But P itself is log base b x, Q itself is log base b of y. We have our result. The third result. You want to prove that log base b of x to the r, the exponent has to jump out. R times log base b of x. Well, let's call P equals log base b of x. What does that mean? B to the P is x. What does that mean? I will take power r, not multiply by r, power r, okay, scratch multiplication. All right, b to the power P to the power r is x to the r. Well, power of power is product of powers. So b to the PR is x to the r. What does that mean? Log base b of x to the r is P times r. I'm rewriting P times r as r times P. R is r, P is log base bx. So you got the result. All right. How do you use these such a theorem? Here is an example. Log base 2 of 48. Log base 2 of 3. I want to find the difference of log base 2 of 48 and log base 2 of 3. Now, if you use your calculator, you will get a decimal number here, a decimal number here. Why? Because 2 to the power. So, for what is 48? Let's see. 2. Let's look, count out the powers of 2. 2 to the power 1 is 2. 2 to the power 2 is 4. So 3 is out. After 4 is 2 to the power 3, 8. 2 to the power 4, 16. 2 to the power 4, 32. 2 to the power 5, 32. 2 to the power 6, 64. So we missed this also. So all we know is that log base 2 of 48 is between 5 and 6. Likewise, all we know about log base 2 of 3 is it's between 1 and 2. So we don't know the exact values, but we can use our theorems. Difference of logs, log base 2 of 48 minus log base 2 of 3 is log base 2 is of 48 over 3. 48 over 3 is 16. Log base 2 of 16 is simply 4. Right? How many powers of 2 in 16? Precisely 4. Okay, so even though you may not know the exact values here, you know the difference of those two values. Likewise, log base 6 of 4, log base 6 of 9. Look, how many powers of 6 are in 4? Not even 1. So this is going to be a small fraction, less than 1. What about this guy? Log base 6 of 9. It's going to be a little more than 1. How many powers of 6 and 9? 1 point something. So I don't have exact values of this, but you can find the value of their sum, right? So sum of logs becomes log of the product. So 4 times 9, log base 6 of 36 is 2.